Welcome back, my fellow COBOL enthusiasts, to chapter 3 of my little online course on COBOL. Today we are going to learn about the control flow in COBOL. That is, we are going to learn how to actually make a COBOL program do something meaningful. We have the following sections today. So first I will review some basic instructions. Those do not exactly relate to control flow, but it's important to cover them at some point to get meaningful input and output, for example. Then we will look at how COBOL handles conditions, so mainly the if-then-else construct. Loops to perform repeated operations over data, procedure calls in COBOL, and finally I'm going to look at the built-in searching and sorting functions in COBOL. Let's start with a review of some basic instructions, some of which we've encountered before. So I will look at the instructions move, stop, run, continue, display, and accept. And as I said, we used some of those before, and their usage is mostly self-explanatory. And I will give some additional informations and from maybe some more sophisticated usage of display and accept to get the complete picture here. Let's begin with the move instruction, which works like this: move x to var, where we assume that x is either a variable or some immediate value, so like a constant number or a given string, and we move it into the variable named var with this instruction that we've seen a few times before. We already learned in chapter 2 how we can use the corresponding clause with the move instruction to move record entries from one record to another if these record entries in the two records have matching names. Now we have to be a bit cautious when moving data between data items of different types. Recall we have different numerical data types, for example, and move will often not cause an error when the types are different. So we have to be aware of what can happen then. If both operands are numerical types, then usually COBOL correctly converts the types, so converts the type of x into the type of var, provided this is possible. So for example, it is not possible if we move a signed numerical type to an unsigned one, because in that case we will lose the sign. So this would be an operation that will not cause an error, but would give us a faulty result. Moving numerical data to alphanumerical types is only allowed for integers or signed integers, but for fractions this will cause an error. And the other way around, if we move alphanumerical data to numerical type, then this can lead to unexpected results. It usually will not give an error, but we should expect the result to be garbage. So we call this undefined behavior. Next, we have the stop run instruction. We already saw this at the end of our COBOL programs. And yeah, this is used to end the current program in a regular manner and return to the operating system. So in that sense, it's comparable to the exit 0 instruction in C. And you can use this at any point in the program when some condition is reached to properly end the program, so it doesn't have to appear only at the end of the program. And we can also exit the program with an error if we use the stop run instructions in the following way: stop run with error n, and n is a numerical error code which has to be a positive integer, and depending on the value of n we can then interpret which error occurred. Then we have the continue instruction, and this one simply doesn't do anything. So it's like a knob in assembly. Now you may ask yourself, why would we have such an instruction that doesn't do anything? This is mainly for readability, because sometimes we have conditional instructions, where in some cases no action should be taken, but we still want to list that case for the sake of explicitness. So in that case, we could simply write, in this case, continue, so do nothing, just proceed with the program as you would otherwise. And for this, it might be useful to use the continue instruction. Now let's look at accept and display. So we have seen those before. And the display instruction is used in the following way: display x1, x2, and so on. So we can supply an arbitrary amount of arguments to display, which are just separated by spaces, or if you want to make it more explicit, you can use commas between the argument. And these are either variables that contain some value to be displayed, or they are immediate values like constant numbers or strings. These items will be displayed in the terminal window. So we run our program from the command line and it will simply appear in the terminal on the command line or just below it. And each of these items displayed here occupies as many characters on the screen as you have defined it in the working storage section or in the data division. So if we have let's say an alphanumeric variable here that we define to have 20 characters, but we assign it a value that is only 5 characters long, then on the screen it will still occupy 20 characters, and the additional characters that are not used will simply be displayed as blanks. Now if we just display it like this, then there will be no spaces between the different output elements, so we have to figure out ourselves where one item on the screen ends and the next one begins. And at the end we will have a line break. So if we have 2 display instructions after another, then they will appear on separate lines. And accept can be used in a similarly straightforward way. Accept var, so where var is some variable, some data item, then we can read the input on the command line and it will be written to var. There won't be any cursor to indicate where the input is expected, so it will just appear under the last line on the terminal. And we can only read one input variable at a time. So unlike display, where we can output several variables or values, with accept we can only read one per each accept statement. There's a special form of the accept statement that allows us to read date and time. So we have these modifiers here: accept from day of week, and from time, and from date. So here I have the proper format for those and an example on how to use these. So if I read today, that would be from date, so the current date. And this is given by 6 numerical characters, the first one being the year, the last 2 digits of the current year, 2 digits for the month, and 2 digits for the day. So in particular, we have no information about the century that we're in when we're using it like this. Some of you might remember the infamous Y2K bug, the year 2000 bug. That was an issue at the beginning of the year 2000 because it was expected that a lot of dates that were simply given as these 2-digit years numbers would cause a lot of bugs in the COBOL software. So this is actually where this bug originated. And apparently when COBOL was designed, they never expected it to run for that long, that you would need 4 digits for the year, and it's still like that you only have the last 2 digits of the year. So if you expect your software to run for over a century, you have to manually work around that. Next we have day of year. So this has 5 digits. First the year that we're in, just like here, and then 3 digits which just give you the number of the day within that year. So this is probably something you won't use that often. Then we have a weekday, which is just 1 digit. It just gives you a number from 1 to 7 corresponding to the current day of the week. And then we have time, which I call it in this record now, which has 8 digits for the hour of the day, the minute, second, and the tenth of a second, ds for decisecond. And this is how we read those. So the current date is except today from date, day of the years except day of year from day, except weekday from day of week, and except now from time. And let's see how this works in an example. Okay, so here I have defined my data structures, my records for the date. And now let's read them with the except instruction. Okay, now I have the date and time values written to these records here, and I want to display them in a reasonable manner. So let's use display for that. Display date. And what will we do? I will first display the year. Then I will, for readability, separate this from the month and the day. This will display the year, the month, and the day. And the time we can simply display in a similar way. First the hour, followed by the minute. And the second, and I will not display the 10th of a second, that would be a bit excessive. And yeah, let's compile this and run it. So yeah, here we see the date. So today is the 19th of November 2023, and it's 11 past 5 in the afternoon. We can actually display the weekdays in a proper manner. First, I introduce a table to contain the name of every weekday, and then I actually have to manually assign the names of the weekdays to this table, and then I can read out the number of the weekday using the day of week with except, and then I can just print the corresponding name in this table. So here I set the values for this weekdays table. And now I can also print the day of the week here. So what this does, weekdays in plural is the table with these strings here, and weekday is the number of the weekday that I read with the except instruction here. So if I use this as an index, then I get the proper string for the current day of the week. And I will separate this with comma from the following date. And yeah, we get this output here. Sunday, the 19th of November 2023. And yeah, you see there's some trailing spaces here because the value in our string, as I said before, is actually not as long as the maximal length. So I have 9 characters and we print 9 characters here. But Sunday does not have 9 characters, so I have some additional spaces at the end. So far, we only read input from the command line in the terminal and also displayed our output just underneath the terminal's command line. COBOL does, however, allow us to use so-called screen-oriented input-output, which is not a very descriptive name, but what it actually means is that we can control where our data is read or displayed on the screen, and we can do some additional formatting for the displayed text. And in order to use this, we have to add something in the environment division of our COBOL program. In the configuration section, special names paragraph, we have to set console is CRT. So CRT stands for cathode ray tube, which is just an old screen in the pre-LCD or LED times. And yeah, this was used to designate screens in the olden days, because back then when COBOL was invented, maybe it wasn't a given that you would display output on a screen, so you could explicitly state this here. And if you use this, then you can control where your text is output on the screen. And note that GNU COBOL doesn't care too much about this setting, so if you just use the commands to place your output manually on the screen and format it in some other way, GNU COBOL at least will automatically switch to this screen-oriented I/O. But I suppose other COBOL compilers might be stricter when it comes to that. So we will see in a minute how we can use this. But first I want to tell you what you can actually do in this screen-oriented display. If we want to display some data x1, we can, for example, use this clause at line L, column C, to display the element at line L and column C on the screen. So we can control the position where it is displayed. Otherwise, it will just be in the first position of the next line on the terminal if we do not use this position clause. And we can also change the representation of the data on the screen. So we can do some formatting of the following type. So we have the with clause, and we have several instructions here with A1 V1, with A2 V2, and so on, where these A's are certain attributes that we can control, and the V's are simply the values that we set for these attributes. And if we display multiple elements at once, then the properties above have to be applied to each displayed item individually. So if we set the position for x1, then we have to also set the position for x2 after that manually. Otherwise, the position of x2 will be taken relative to the one of the element before it, and so on. And the attributes, so we had these AV pairs, attribute value pairs for the with clause, are the following. With bell, this causes a beep when the display instruction is executed. With blink, makes the display text blink. With underline, underlines the display text. With foreground color V, so here we can actually set a value, sets the color of the display text to the value V. And we can choose between these 8 values here. 0 is black, 1 is blue, 2 is green, and so on, until we have 7, which is white. We can also set the background color in the same way. So with background color V, and then we can use one of these values here to set the background color. With reverse video, this inverts foreground and background color. And with size n, this sets the length of the displayed text to n characters. So if we do not use this option, then the length is simply the size of the data item we display when it was defined in the picture clause. If the length of our data item is smaller than n, then we simply fill up the displayed text with characters on the right. And if the length of the displayed element is actually larger than the size n here, then we truncate characters from the right of the displayed element. Depending on which COBOL standard you use or which compiler you use, there are other attributes available, but I found these are pretty much the only ones that work with GNU COBOL, so I'm not going into other possible attributes. What I want to do next is to create an input mask for a personnel record. So you might recall from a previous chapter, we had a personnel record with a few entries as an example. And now I want to create an input mask for such a personnel record where I place some text fields where you can enter the data. So the first thing I want to do is add some constants to our, which I will use to display color. So here, these are the numerical constants for the different colors I can use in the screen-oriented I/O. Then I need to add the data structure for the personnel record that I want to first read and then display. So you might recall this. We used this in a previous example. First name, last name, street, city, department, and salary. And something I also want to use now to make the date look a bit more appealing. I add a constant 20, which I call century, to be displayed before the 2-digit year value. So we actually see 2023 instead of just 23. And yes, I am well aware that we actually live in the 21st century, but I use 20 here to get the proper output, and I don't want to have to subtract 1 every time I have a display with the year involved. And you need to be aware that you need to change this constant here in your source code every 100 years or so to make your program stay up to date. Now I will first add this here. So here I want to display 2023 instead of just 23. So I will simply add century here, and because there are no additional characters being output between the century constant and the year, they will be displayed as one number. Now let's get started with creating the input mask for our personnel record. And I will actually use the display of date and time within that mask. So I will just leave this stuff here. The first thing I do is I want to display a nice header for my input mask. So enter personnel record. And this I want to place at the top of the mask and in the center of the screen, or at least near the center of the screen. So I use the at line 1, first line, and column, let's say 30. I mean, the screen size of course varies if I resize my terminal window, but in a classical display we would have 80 columns in total, so 30 should be somewhere near the center. And I set the foreground color to something very noticeable, let's say red. So if I use red here, then I will actually use the constant red defined up here. So this is the same as writing with foreground color 4. And I will also set the background color just to show you how this works. Let's say the background color is white. Okay, next I want to display the date at the roughly the upper right corner of the screen. So I will put this at line 1, column, let's say 70. Maybe I'll get rid of the time, because this just puts out the constant time when it was read, but it doesn't update it. So having a not changing time on the screen is maybe not so helpful. So let's remove that. And now I want to display some text fields where we can read the attributes of our record. So these attributes here, I need a text field to print out each of these attributes. Display first name at line, let's say 4. So this should be somewhere below the heading. So the header was here. So let's say we go down by 3 lines to line 4. Begin at the left of the screen at column 2. Then we read the last name. And add some spaces here to align these columns here to make it look a bit nicer. And let's say we leave an additional line between these input lines so it doesn't look too cramped. Next we read the street. And then again 2 lines, so line 8, column 2 now. Then city at line, you guessed it, 10, column 2, display department at line 12, column 2, display salary at line 12, column 2. Okay, now we will have a mask that will allow us to read the to display all these fields at this point. Oops, there's a Y missing. At this point, we can't read any data, but I will change that in a few moments. Let's first have a look how this will appear on the screen, and we mustn't forget to include the appropriate environment division at the beginning of our program. So here I copy in the environment division, configuration section, special names, and the option console is CRT, which tells COBOL that we use screen-oriented input-output. Yeah, let's see how this will work out. Maybe increase the size a little bit. No errors, so that was good. Yeah, so this is what it looks like now. First of all, you notice that with screen-oriented input-output, we clear the screen of anything that was in the terminal before. Here we have our header with the foreground color red and background color white. Here we have the date with the 2023 now, so here the 20 comes from this century constant that I defined. And here we have these fields: first name, last name, street, city, and salary. Yeah, and GNU COBOL has this annoying feature that whenever you use screen-oriented input-output, you get this annoying line here, end of program, press a key to exit. I really wish they wouldn't do that, but they do. So yeah, we press a key to exit and return to the terminal we were at before. Now let's see how we can format our inputs for the screen-oriented I/O. So the screen-oriented accept works very similarly to the display. So again, we can use at line L column C to tell COBOL that we want to read our input at this line and this column. So when you type the input text, then the letters will appear at this position here, rather than just at the next line of the terminal. And again, we can use certain attribute value pairs to format our accept instruction. And when we read a numerical variable, then the input from non-numerical characters will automatically be blocked. Now the attributes we can use with the with clause for the accept instruction are, first of all of the ones we could use for the display instruction. And some additional ones exist, for example with secure, so just the attribute secure, no value. This is, for example, in a password field. You can use this to prevent the input characters from being displayed on the screen. So you will just see some asterisks instead of the actual letters that you type. Then you can use with left justify or right justify to align the text input fields to the left or the right. You can use with full, and this requires the input field to be either full or empty. So either you leave it empty or you enter the amount of characters that correspond to the size. And yeah, if you don't fill it up, then the cursor will remain in the current input field after hitting enter. So you will not be allowed to move on from the accept instruction. Then there's with prompt character C. You can use this to pre-fill all the characters in the input field with a given character C. With required means that this input field must not remain empty, so you have to enter something before you can move on to the next instruction of your program. And unfortunately, even though these are all nice features, GNU COBOL at the moment appears to only recognize the secure attribute out of all of these. So if you were to use any of these, they would have no effect. Now let's get back to our personal record input mask and add some accept instructions to actually read data for this record. We have used these displays to display the input fields, and now for each of these displayed input fields I want to write a corresponding accept statement to actually read a value for these entries here, and these values should then be written into our personnel record here. So we begin with the first name in personnel record. So I just use this for explicitness because we don't have first name in different records. I would not strictly have to use this in clause here, but yeah, as I said, just for readability, I use it here. Now, just for the fun of it, let's make this a really horrible looking input field. So we can try out all these options that this screen-oriented I/O gives us. So let's reverse the video. So we change foreground and background color with foreground color green. Oops, stupid autocomplete. With size 80, so we have an 80 character wide input field with bell, because why the hell not? Let's have a little bell when we enter data here. And let's have it blink while we're entering it, so our eyes get really burned out looking at it. And we want to place this, of course, behind this text here. So this is line 4, column 2. So we have to place this on line 4 as well, but the column should be, well, so that it appears after this string here. So let's just say we go to column 14 to be sure. Now let's do the other ones, except last name in personnel record, and yes, this has to go, of course, behind this. So we go to line 6 now, and again column 14, and yeah, the rest I will just copy this in. So we get the full input mask. So again, we see our input mask here that we had before with the header and the date. And now we have this weird looking input line to enter the first name. Yeah, you see we had this little beep when the program started. That was when this accept instruction began here. We have the foreground color green, but because I reversed video, it's actually the background color that's green now. We have size 80, so it's a really big line. And when I enter text, we will see that it's actually blinking because of the with blink. So yeah, so we enter Homer. Then once we've entered that, we're done with this accept. We get to the next accept instruction where we enter the last name. Let that be Simpson Street 742 Evergreen Terrace in Springfield. And let's just make something up for the salary. And that's it, we're done. Now, one thing I want to add now is once I've entered the data for the personnel record, I want to display the full personnel record. And I'll just copy that in because it would take too long to just type it all explicitly. So here I have some more display instructions. And again, I want to challenge your eyes a little bit. Again, I have a heading here, which is displayed again in the center, just like the original heading for the enter mask. But of course, a few lines below, Now I have a really disgusting combination of foreground and background color, and I have it blinking, so yeah, get ready for some visual pain. And then I simply output the data that I just entered before. So let's see how that works. Notice the little bleep we just had. Okay, just do it again. Homer Simpson 72 Evergreen Terrace Springfield 5. I don't really know why this is there, but yeah, so here we have the output mask. There was definitely something wrong with the salary here, because it's displayed as 00. That should not be the case. But all the other data was transferred correctly from where we entered it here to the output. Yeah, department and salary is somehow... Oh yeah, I missed the department thing here. So that's why it's all mixed up. Oh yeah. This should be 2 different lines, so that should do it. Department is safety. And now it all looks good. So we have our unpleasant view personal record heading here, which you can see foreground color green, background color violet, with bell with blink. So that's why we hear this little beep when the personal record is displayed at the end. And yeah, here's all the data we had from the previous input mask. And that ends our program. One last thing to mention when we are displaying strings. As I said before, COBOL strings are of a fixed length, namely the length you assign to them when you define them in the working storage section, in the picture clause. And therefore, when they're displayed or when you use them, they will usually be filled up with blanks if the actual value contained in the string variable is smaller, or the length of the string contained in the variable is shorter than the maximal fixed length. So if you want to remove those additional strings, then you can use a certain instruction in COBOL, which is the built-in trim function. You can use it like this. So if s is your string variable, or it could actually be just a given string, even though it wouldn't really make sense to remove spaces from a constant string. Anyway, if this is your string variable, then you can use function trim s with either trailing or leading to remove blanks at the end or at the beginning of the string. And this is actually important to know, because sometimes you actually have to do this if you compare the value in a string variable with some constant string. And if you still had these blanks inside your string variable, then the comparison would fail, even though the string is actually the same as the one you want to compare it with. So in that case, you will really have to trim the string to get a proper comparison. And I will use this function a few times in this chapter, so keep in mind that this is what it does, removing unnecessary blanks from a string variable. Next, we're going to look at conditions and conditional code branches in COBOL. So like most programming languages, COBOL allows us to evaluate conditional statements and change the flow of our program accordingly. There are 2 instructions to achieve this in COBOL. The first one is the if statement, which is quite familiar from other programming languages. And this one just lets you choose one out of two paths depending on whether a certain condition is met. And if you want to evaluate more paths and more possibilities for that condition, then you can use nested if statements to do that. There's also the evaluate statement, which is a bit more complex than the if statement, I would say. And this can be used either as a switching instruction, similar to the switch in C. And for this we can evaluate a variable and continue in the code depending on the possible values of this variable. Or we can use it as a more convenient evaluator for multiple conditions than the nested if statement. So here we have the ordinary if statement, or if then else as it's often called, which looks like this. We have if some condition is satisfied, then we execute the code here. Otherwise, well, we have the optional else statement. Otherwise, we could execute some code following the else statement, or if we omit that, we'll just do nothing in the other case. There are two versions of it, syntax-wise, because we can end it just with a period, or we can use an end if to end this if statement. And note that we are not allowed to use periods within the if statement, because in COBOL logic this whole thing is considered to be one sentence, so there may be only one period at the end to end it. The logic here is that if the condition is satisfied, then we execute the code following then, either up until the else branch, or if we do not have an else branch, then we just execute the code up until the next period or the end if statement. And obviously, if the condition is not satisfied, then if we have an else branch, we execute the code in the else branch. Otherwise, we just continue after the period or the end if. Let's see a little example of that. What I want to do here, I ask the user to enter a positive even number, which I read in with accept, and then I want to check if this is truly a positive and an even number. And I'll just do this using some if instructions. So if n is less than 0, so we check if it's actually a positive number, and if it's negative, then we give an error. And in that case, we end the program. And I will always use an end if to end my if statements, just for readability. Also note that, strictly speaking, COBOL does not require you to use a period after the end if. I'll just use that because I think it looks more consistent with the whole COBOL syntax. But some compilers might actually complain about having an end if together with a period. This should probably be less or equal 0. Okay, now I have checked if my number is positive, and now I will check if it's an even number. So what we do is we divide it by 2. And you see above I've defined the dummy variable, so I'll just take the integer part of that division and put it into the dummy variable, because what I'm interested in is the remainder, rem, and I check if the remainder is 0. This means that n was an even number. And here you already see a few of the conditions that we can have. So here I had an inequality, here I have an equality. So if the remainder is 0, then we do indeed have an even number. Praise the user for getting that right. But if not, then the user gets scolded and reminded that even means the number has to be divisible by 2. All right, let's try this out. Compile it. First, let's put in a negative number. Yeah, so this condition here is satisfied, and we get this error message here, and the program terminates. And I put in an odd number. So here, this condition is not satisfied, so we go into the else branch and get scolded again. Now let's do it right. 4 is a positive even number, and we get praise for getting that right. So here, this condition is not satisfied for 4 because it's positive, so we don't do anything here. And here we indeed get the remainder of 0 on division by 2, so this is satisfied, and we display the good job message. Now let's take a closer look at the types of conditions that we can formulate in if statements. So there are several components to that. So there's either one conditional variable. So recall we had them in chapter 2. These are the ones defined on level number 88, where we can have one variable that may assume different states or different ranges of states. We had this example with the ghost town, the village, and the city, depending on the population size. And yeah, depending on the number we assign to this conditional variables, the conditions in it were either true or false. So we could use those in an if statement. Or we have two operands, which can be some of the following. Either we have variables, so there could be data items, records, or tables, or constants, like constant numbers or strings. We can have arithmetic expressions as operands in an if statement. And yeah, these could be the same ones that we use in the compute instructions, so they can actually be rather complex. Now, one thing you have to consider when writing down arithmetic expressions is that if you use a subtraction sign, so the minus, between two variables, then you require spaces between the variable names and the minus sign, because otherwise COBOL might mistake it for a hyphenated variable name. So I tripped over that a few times and was a bit confused what I did wrong. But I'm telling you now, so you don't make the same mistake. Other things that can appear as operands in an if condition are one data item and one character class for data items, which are of type usage display. So this is basically used to check if usually a string that you give to the if condition satisfies a certain format, and I will discuss that in a moment. And then another option is to give one numerical operand and a sign. So that's basically just testing the sign of a number. Then, in addition to the two operands, we need a comparison between these two operands, and the operators we can use there are the usual suspects. So we have less than, less or equal, equal, greater, equal, or strictly greater as possibilities. And in COBOL we can even write out these operators in words. For example, for the greater or equal operator, we could write this out as greater than or equal to. Now, for obvious reasons, I strongly want to discourage doing that. It would be painful to read. And then, of course, the truth value of the condition in the if statement is determined by how the left operand and the right operand compare. And then, if the condition is true, we do what's coming after the keyword then. Otherwise, we do the else branch or we don't do anything. Now, this may seem obvious, but since all variables in COBOL are singletons, so we don't have multiple instances of records or something like that, comparisons are always done by value and never as by reference, because that doesn't even make sense in COBOL. So this means if I compare two records with one another, I will go through each single one of the attributes for each record and compare the values of these attributes with one another. And if they all match up, then the records are considered to be identical. Let's see some more examples for using these conditions. What I want to do for my next example is I want to check if a given point with coordinates xy lies within a circle of radius r, where the radius is randomly determined. So here I have this random function which I multiply by 100 to get a reasonable large enough number for my radius. And then I want to have the user enter two coordinates, and I want to check if that is within this circle. Now I introduce the following variables for that, x and y as the coordinates. You see it's signed numbers with 4 digits, 2 decimal digits. R is the radius for my circle, which is a positive number of course, and seed is just used for the random function. Now, first we need to have the user enter the two coordinates for our point. And now I want to check if the point with these coordinates is indeed contained in the circle of radius r. So I use an if statement, and now I use a built-in function, so an arithmetic statement to compute the length of the vector pointing to the point xy. And this has to be smaller than the radius. Okay, so this is just applying Pythagoras to our point with coordinates xy, and if this is less than r, then we're good. Remember, I'm not allowed to use a period here. This would be wrong, because then the if statement would be ending at this place already, so I would not be able to follow up with an else branch. But this is for the case that this condition here is not met, so that the point with coordinates xy is indeed outside of the radius r. Abbreviate this a little bit so I don't run past my 80 column limit here. Sometimes, unfortunately, you have to do that in COBOL. And if let's check this. Okay, first we have a positive number again. Let's ignore that. So our random radius is this one. So let's say I take the point with coordinates 10, minus 10, and yes, that is certainly within this radius. Don't forget the last 2 digits here are the decimal digits. I just have a binary value here, so it's not properly formatted for output in COBOL. So this is actually 10 and minus 10 here. Let's take another one. Now we have a radius of 55.99, so let's take x to be 100, so this one should definitely not be within the circle. And yeah, we get the else branch here. And this is an example that illustrates that you can have a rather complex expression as a condition in your if statement. So you can use arithmetic expressions, and you can even call the built-in functions for those. And just a few minutes ago, I told you about 2 special kinds of comparisons or choices of operands for those. And the first one is the character class test. So assume we're given some data item X that is of type usage display. So it could be a string, an alphanumerical variable, or it could be a number that is defined with usage display. Then we can use a condition of the form X is C, where C is a so-called character class. So C could be alphabetic, alphabetic upper, alphabetic lower, numeric, or a user-defined class. So, and these classes here, well, that's clearly only characters, and here we only have uppercase or only lowercase characters. Numeric means it has to be a number, so you could use this, for example, to test if a string actually represents a number, or you can define your own character class to test against. And to do that, we would have to declare it in the special names paragraph, in the environment division, in the configuration section. So here's an example of that. So here I define my own character class, which I call alpha and punctuation. So that's the alphabetic characters, A to Z, lowercase and uppercase. So that's given by A through Z lowercase and A through Z uppercase. And then I also include the punctuation characters. So period, comma, colon, semicolon, the space, question mark and exclamation mark. So I could test a string variable now against the class alpha and punctuation. And if it contains only alphabetic characters together with punctuation signs, then it would pass this test. Let's look at an example for that. So the first thing I do is I create an environment division, configuration section, special names paragraph, and I define my alpha and punctuation character class here. And then I introduce 2 more variables in the working storage section. That is txt and num. So here I have an alphanumeric variable and 1 binary numerical variable. The idea is that I let the user enter a number, put it in a string, and then I actually check if it is a numerical, if this string represents a numerical variable. Now, naively, I would do it like that. If txt is numeric, then I do something, tell the user, yeah, great, you entered a numeric variable. But then we would get a problem because remember that I told you before, if we have an alphanumeric variable and the string I enter for its content is not at the full length, not the same amount of characters that are reserved for it in memory, then this string will be filled up with blanks. And these blanks would appear as relevant characters in this comparison. And then I would never pass the test of it being numeric because the blanks are not numeric characters. So I cannot use them for that. So I will trim this string, meaning I will remove all the trailing blanks. And then it makes sense to do this test on whether the content of the trimmed string is numeric. And in this case, if this is true, if the string entered here, so I actually do that here, if the string entered here indeed represents a number, I will display this here. And yeah, let's do some more tests just for the fun of it. I can then compare the string number, if you like, to the number that I entered here. Type safety go to hell. And if it's smaller than the number I entered, then I write that. This is just to give you some example of a nested if condition. Okay, see what we do here? No, I can't use the period here because then this would terminate the outer if condition. Must not do that. So yeah, I have my first condition here, checking whether the entered string is numeric. And then if it is, I compare it to the number that I entered here. And of course, if it's not numeric, it makes no sense to do that. So now I have the else for the outer if condition. So in the case that my variable does not contain a number, and also trim the string here just to have a nicer output. Put it in parentheses, in quotation marks. And have some more nested conditions. So remember that I defined my own character class up there. So now if it's not a number, then I test if it's at least contained in my self-defined character class. So this is txt, is alpha and punctuation. Here I actually don't have to trim it because I included the blanks in my character class. You could trim it if you use a different character class, of course. Whew. Yeah, this is a rather complex nested statement. Let's compile this. Okay, let's enter a short text. So I will just enter some number here as a text. Now I'll enter a number. And indeed, if we trim this string, so here we actually have the untrimmed version, then it is numeric because all the characters appearing in it are numerical characters. So this condition here is satisfied. So I print out this string here. And then I make the comparison whether it's less or equal to the second value I entered, but somehow COBOL doesn't get that right. So yeah, comparing numbers and text strings is not very meaningful. So we should probably augment this. Okay, now I will try to get into the second branch here, so I will enter a text that is not numerical. But I'll use an exclamation mark, so it should still be within the alpha and punctuation character class. And indeed, we find out it's not a number. So this test here fails. So we get into the else branch, but this test here is successful because we only have alphabetical characters and punctuation marks inside our string. So we get this displayed here. The other special kind of comparison we can do in an if condition is a sign test. So suppose x is some numerical operand for a comparison, and instead of writing x greater 0, x equals 0, or x less than 0, we could do this explicitly with a sign test by writing x is positive, x is 0, or x is negative. Now, whether you think this is better style than this is up to you. Personally, I would prefer this version here, but just know that COBOL allows you to do this. And then we can use composite conditions. So we can take our simple conditions and turn them into more complex conditions by combining them using the so-called logical connectives, not and or. So the negation of a condition, which is true if the original condition is not true. The logical and of two conditions, which is true if and only if both of these conditions are true. And the logical or of two conditions, which is true if and only if at least one of those two conditions is true. And if you want to learn more about the theory of these logical connectives, I want to recommend chapter 1 of my own course, Introduction to Mathematics, on my second YouTube channel, Mathflix. But here I do not want to go into that, so I will just assume you have some basic understanding of these logical connectives. And the priorities when evaluating the parts of composite conditions is given by this table here. So with the highest priority, we evaluate arithmetic expressions, and you might recall from the previous chapter where we studied arithmetic expressions how the priorities of the different operators within the arithmetic expressions are ordered. Then the next highest priority is given to simple conditions. So the composite conditions are composed out of several simple conditions. So these are evaluated in this order: comparisons, character class tests, conditional variables, and sign tests. And finally, the lowest priority is given to these logical connectives in this order here. So first negation, then logical and finally the logical or. Now I want to show you an example of an if statement that uses composite conditions. And remember, I just had this example where we could enter two coordinates, x and y, and then we would test if the point with these coordinates is contained in a circle. I will just build on that. I'll use the same coordinates x and y, and I will check if the point with these coordinates is contained within a triangle with the vertices with coordinates -1, 0, 0, 1, and 1, 0. So if you can't picture that, maybe take a piece of paper and draw a little coordinate system and sketch these points so you have an idea what this triangle would look like. And as a test, whether our point xy is contained in that triangle, we can do some composite conditions here. So remember what I said before. Here I have 1 minus x. If I were to write it like this, I would get an error, because then COBOL would mistake it for some variable name with a hyphen, so I have to put in the spaces here. Okay, so to test whether the point lies in this triangle, I first check if x is greater or equal to 0 and y is greater or equal to 0. So we're in the first quadrant of our coordinate system, and then I check if y is below 1 minus x. So if it's under the side of the triangle. Or alternatively, if we're in the opposite quadrant, I check if x is negative and y greater or equal 0. And here I have to check if y is less or equal 1 plus x. And we never have the case that y would be negative, because then we could not be in this triangle here, because all the y coordinates in this triangle have to be greater or equal 0. Now, if this is the case, then I will display something. I'll just follow up on the printout from our circle test, so I'll have these dashes to separate it, and if my point is not contained in this triangle, then I will just not print anything. So here we have a rather complex composite conditions. We have several inequalities combined with and 2 of such conditions combined with a logical OR. And let's test this. I don't care about the radius now, but I want to make sure our point is within this triangle. So maybe we just, let's just take one of the vertices of the triangle. So I take x equal to 1, 1 equal to 0. And first we get, yes, it's within that radius. And also we get that this condition here is satisfied, and we get the confirmation that this point is contained in the triangle with these 3 vertices. That's it for the if statement. Now let's have a look at COBOL's evaluate statement. And this one allows us to distinguish between different cases for the value of a given variable, or even multiple variables, as we will be seeing in a moment. And this is vaguely similar to C's switch statement, but it allows us for many more variations. So it's a rather complex statement. Let's first look at a simple case. So here we have the statement evaluate x, and x can be many things. It could be a variable, or even more generally an arithmetic expression involving variables, or it could be a logical condition of the same type we would use in an if statement. And in particular, x could simply be true or false, which are like the most basic logical conditions you can imagine. And then this evaluate x is followed up by one or more statements of this form: when, y, then do something. And y here is a possible value that x could have. So the idea is we look at x, and if x takes the value y, then this is what we want to do in this case. And we can, as I said, have multiple of these when statements. So depending on which of those multiple possible values for x we do different things. Now it's possible that we have multiple of these when cases matching the value of x, so multiple of those could be true, but COBOL will only execute the first one where we get a match. So you have to keep that in mind. If you have multiple matching when cases, only the first one will be executed. And the whole evaluate statement is either ended by a period or by an end evaluate. So that's analogous to the if statement. We also have a default action that we can take if none of these when cases matches x. So if all of them fail, then we can do when other, and here we just have our default action that we would do in this case. As I said, evaluate is a bit of a complex statement, so it might be confusing, and looking at examples probably makes the whole thing a bit clearer. So here I have an example that will simply print which day of the week it is. So I have a weekday variable that I will read with accept weekday from day of week. We've seen that before. Then I will display today is and evaluate weekday. And depending on which number it is, I'll print Monday, Tuesday, Wednesday, and so on. So that's the numbers 1 to 7. And I also add in a default statement that never should be the case, actually, because if our weekday is anything other than the days from Monday to Sunday, time is out of joint, the rapture is at hand, we're doomed, so we should inform our user accordingly. Let's see this in code now. So here we have the same example in code, and let us compile it and run it. Today is Monday, and indeed I am recording this video on a Monday, so that worked out well. And let's look at a second example, and here I want to bring back my population size variable from the previous lecture. So you recall this, we had population size, and then I had these conditional variables here which are true depending on the value that I assign to population size. And in the previous chapter I evaluated this with a nested if statement, and it is probably more efficient to use an evaluate to check this. So let's see how that works out. So the first thing I have to do is I have to copy my conditional variables for the population size into the working storage section. And then I want to check which kind of settlement I live in, depending on the population size. So I use the evaluate statement for that. And this may look a bit odd because now I evaluate true. So I evaluate this logical condition, which is simply true. And then I write it like this: when ghost town, display you live in a ghost town. Okay, so this, you get what we're doing here. We evaluate to true, and then when ghost town is true, we display this. Next is when village is true. We display this. And so on. We'll remember that only one of those can be true at the same time. This is just the nature of the conditional variables. So we evaluate to true, and then whichever one of them actually is true will get displayed. Let's say 0. Yeah, we enter 0 for the population number, and that means here the ghost town is true, and this will be displayed. Let's try it with a different, say 100,000. This means we live in the city, so this case is true, and the other ones are not. And this is actually a use of this evaluate statement that you see quite often, even though it's a bit odd when you see it for the first time. So yeah, be aware of that. Now these were the simple evaluate statements, but we can also have a more complex one where we actually evaluate multiple conditions, and the syntax for that is evaluate x1, also x2, also x3, and so on. And then the conditions or the cases for these multiple conditions are formulated as follows: when y1, also y2, also y3, and so on do something. So for each one of these conditions that we evaluate here, we must have a matching entry in the cases. And if all of these match, so if y1 matches with x1, y2 with x2, y3 with x3, then this case is true, and we do whatever code we have following up this statement. And here you of course have to make sure that each of the y's that appear in your cases, in your when cases, are of the appropriate type for the different conditions that can appear up here. You can also have a case where you want to ignore one or more of the conditions appearing up here, and then you write the keyword any instead of a certain value. So for example, when you write when y1, also any, also y3 do something, then this case gets executed if x1 evaluates to y1, so these two match, if x3 evaluates to y3, and for any other possible value of x2. So this is basically ignoring the value of x2, and we only look at x1 and x3 if they match these values here. Let's see an example for that. I first define 3 numerical variables, and then I just want to do some arbitrary conditions, test some arbitrary conditions on these 3 variables, where I first allow the user to enter the values for them, and then I use an evaluate statement to show you how you can evaluate multiple conditions. So let's say I just take x squared minus y with the spaces around the minus less or equal to y. So we have a comparison. And as a second condition, we simply take the value for x. When true, so this is a logical condition because of this comparison. So if this is true, if x squared minus y is less than y, also let's say any value of x, then we display this fact here that x squared minus y is less than y. And otherwise, when this is false, and let's say x, here the second condition we evaluate, x is less than z, we display x squared is greater than 2y and less than z. And in any other case, we display whatever is the case then. So this is just really some arbitrary conditions that I just made up. they are not very meaningful. Let's maybe format this a bit nicer. Let these align. Yeah. We compile, we evaluate. I enter 3 numbers, let's say 12, 3, and 8. And we end up in the third case. So you can check this. Yeah, this is false, but x is less than that. It's not less than that. So we do not get into this condition, but rather in the other condition, and we just display whatever. Maybe try another one. 3 numbers. Which one? 2, 4, and 6. And here we have the first condition satisfied, so x squared minus y less than y is true. So we ignore the value of x in this one and display this here. Maybe check this. X squared is 4, minus 4 is 0, and that's less than 4. Yeah, this is true. So here we have an example of using 2 conditions or 2 statements to evaluate in our evaluate statement, and the cases matching the different possibilities for these 2 conditions or expressions here. As a final remark on the if or evaluate statements, let me say that we might get into the situation where we have a branch, for example in a nested if statement or one of the cases in an evaluate statement, that should not result in any code being executed, but we simply might want to list it for readability, for completeness, to explicitly list all the possible cases. And what we can do here is either use the continue instruction that I introduced before, which wouldn't simply do anything, or you can also use the next sentence instruction to continue execution after the next period or the next end if or end evaluate. Now, in most cases, those 2 will probably be equivalent, but there are situations where they actually result in different behavior. For example, if we are in a nested if statement, then using continue would simply result in going 1 up in the level of the nested if statements, whereas using next sentence would result in us leaving the whole if statement at once. So even the outermost if statement would be left then. So keep that in mind, that you can use these 2 statements in a different sense when you have nested conditions. Next, we will be looking at loops in COBOL. Just like practically every other programming language, COBOL allows us to execute a segment of code, which we call a loop, multiple times in a row until a certain condition is met that tells us to continue with the code after the loop. Now we distinguish 2 types of loops. Firstly, the for loops. Those repeat the loop depending on counting an index up or sometimes counting it down until a given limit is hit. So until the index reaches a certain value, and then you stop the loop. The other type of loops are so-called while loops, and those repeat the loops as long as a certain condition holds. So for every loop, every iteration of the loop, we check the condition if it still holds, and if yes, then we perform another iteration of the loop, and we might either check this condition before we enter the first iteration of the loop or after each iteration of the loop. We can implement for loops as special kinds of while loops, but for clarity, I think it's better to distinguish the 2. And we can formulate while loops in a logically equivalent way by making them into until loops. And here we perform the loop iterations while a given condition does not hold. Okay, so we say perform the loop until something holds, and as long as that something does not hold, we will be in the loop. Both types of loops, for and while loops, or rather until loops in the case of COBOL, can be realized in COBOL via the perform statement. And once more, this is a statement that includes many different functionalities depending on which parameters we give it, so it can be quite confusing, but it is also very powerful. So let's explore that. Now, the simplest for loop that we can have in COBOL is implemented like this: perform n times, and this then followed by the body of the loop, by the actual code that is executed in each iteration of the loop. And this body will be ended by either a period or by the keyword end perform. And here n can be either a constant numeral or some numerical data item. Now it's important to understand how n is used by this loop. So the value of n, if it's a constant or if it's a variable, is read at the beginning of the loop, and then the value it has at this point in program execution is taken as a fixed number for the loop iterations that we perform. So even if we change n, if it's a variable, during the execution of the loop, that will not affect the number of iterations that the loop performs. And in this simple form of the for loop, we have no way of accessing the loop counter. So COBOL internally notices that it has to perform the loop n times, but we have no natural way of reading out which iteration of the loop we're in. So if we were to do this, we would have to introduce a separated data item that we explicitly increase in each iteration to keep track of the numbers of the iterations. And here we have our first example that we want to explore. This is a simple for loop which just counts from 1 to n. And I want to compute the factorial of a natural number n. So the factorial, as you might remember, it's written like this: n exclamation mark is just the product of all the numbers 1, 2, 3, blah, 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 up to n. And this is the code in COBOL for this. So we define n, which is the number we give as an argument, and fac should be the factorial of n that we get in the end. Then we enter a value for n. We initialize fac with 1. And then we have this loop perform n times. And what we do is we simply multiply our end result by n. And then we decrease n by 1. We have to do this because we cannot access the loop counter, so I have to explicitly decrease it. But also, this will not change the number of iterations because the initial value of n is already taken at the beginning of the loop, and if I change n afterwards, this will not affect the total number of iterations, so I will get a correct result. Now let's verify this. So here I have defined my two variables, n as the input number and fac as the factorial of n. I will have the user supply a value for n here. And now I can write my code to compute the factorial. So I initialize fac with 1, and then I perform n times this loop, compute, multiply our intermediate value by n. Then we decrease n by 1. And as I said before, this will not affect the number of iterations of the loop. And then I'm done. So at the end I just display the result. And together with this display here, this will give a meaningful output. So let's try this out. Yeah, so I enter the number 4, and then I get as output that 4 factorial is 24, which is in fact correct. Lovely. So we've seen the simple for loop, the counting loop, and now let's see how we can realize until loops in COBOL. For these we also use the perform statement, and we write it in the format perform until C, again followed by the body of the loop until we reach a period or the and perform keyword. And here C is a certain condition, so the termination condition for our loop, and it is tested before each iteration of the loop. So as long as C is false, the loop will be executed, and before each iteration C will be tested again. And if at some point C becomes true, then we will execute with the code after the end perform statement. One thing to consider for this condition here, this is a little bit less flexible than the conditions we could put in an if statement. So here we could have comparison operators and logical connectives, but we cannot put arithmetic expressions into this condition C. So COBOL could not understand this. This you have to keep in mind. We can also have this loop run where we test the condition after each loop iteration, and for this we write perform test after until C. So this means that we will not test the condition before each iteration, but after each iteration. We could also write, instead of test after, test before, and this would be simply equivalent to the default. So if we put this in, it would just be for more clarity, but it wouldn't really change anything compared to this one here. Now we have an example for the until loop, and I want to compute the Collatz sequence with an until loop. And this is, it looks a bit complicated. It's actually a classical computer science or mathematics problem. So for any given positive integer x0, we define the following sequence. So the n plus first item in the sequence is either 1/2 times the nth entry in the sequence, if that one is even, or it is 3 times the nth entry in the sequence plus 1 if the nth entry is odd. It is in fact an open problem to decide whether for any possible starting value x0, this sequence will eventually run into a repeating cycle 4, 2, 1. So you can test this if at any point you have a value xn equal to 4, the next value will be 2, and the next value after that will be 1. And if you have 1, then the next value will be 4 again, and then it will be 2 again and 1 again. So once you reach 4, you will always have these 3 values repeating. And yeah, as I said, it's an open problem if every input value x0 eventually leads to such a cycle, or if there are actually some values for which that does not happen. And if you can find a solution to that problem, you will be quite famous. But for my example, I will assume that we always reach such a cycle, and in fact that will be the termination criterion for my loop. So let's look at this example here. I will start with some value x. So I'll have the user enter the starting value, and I will perform until x equal to 1. So I will run the loop until I hit the value 1. And then I will display first the current element of the colored sequence. And then I will test whether my value x at the moment is even. So I will take the built-in function mod with the division by 2. If the remainder of that is 0, then it's an even number. In that case, this would be this case here. In that case, I divide it by 2. Otherwise, it obviously has to be an odd number, and then I would multiply it by 3 and add 1. And this I repeat until I hit the element 1, and then I will output the message that we've reached our cycle 421. And of course, I could quit the sequence already when I hit the number 4, because I would know that then 2 and 1 would be the next elements. But just want to have the complete sequence up to the element 1 just for explicitness. So I let it run down to the element 1. The first thing I do for this example is I define my new numerical variable x that I will use for the colored sequence, and down here I will have the user enter my initial value. And the first thing I will do is actually not start the loop, but I will check that we have a positive integer. So I will display an error if our number is less or equal 0. Okay, this is just a sanity check. And yeah, actually, since this is a positive number anyway, I don't really have to check that it's below 0, because I can't even enter negative numbers. But 0 would be possible, and I don't want that. I have my perform loop, so I perform until x is equal to 1. I display x with a little space in front of it. And now I test whether x in the current iteration is odd or even. So I take x modulo 2, and if I get 0, then it is even. So what I do here is I divide it by 2. Otherwise, it has to be odd. Then I multiply x by 3 and add 1. I forgot the end perform, so after the loop, I just output the result. Okay, this is just my factorial again. Now I enter the positive integer for the colored sequence. Let's take 10. And you can verify this with pen and paper if you like. We have 10, 5, 16, 8, 4, 2. Then we have reached the element 1. In addition, COBOL allows us to combine the features of a for loop with those of an until loop by introducing a counter variable. And we can do that using the perform statement in the following manner. Perform varying n from n0 by I until c. So let's take that apart. varying n. Here n is a numerical data item or an index variable for a table. So recall from chapter 2 where we learned about index variables. And 0 is a number, which is the initial value for n, so the starting value. I is an increment by which we increase n after each iteration of the loop. So we start for n with value n0, and every time we go into another iteration of the loop, we increase it by this value I. And again, until c, the c is the condition that makes us terminate the loop once it is satisfied. So we have an until loop with this termination condition, where in addition we have a counter variable that we increase in a certain manner where we start from a certain value. Now, usually you would expect that the termination condition is in some way related to this counting variable, so that after reaching a certain number for the counter or some number depending on the counter, we terminate the loop. But this is not strictly required. So this n here could be completely unrelated to c. And we can use additional parameters with this version of perform. Again, we can use test after, just like we did before, to test the condition c after the loop body, not before. And it is also possible to create nested loops by having multiple of these clauses here combined in the same perform statement. So I could follow this line here with an additional clause varying n prime from n0 prime by I prime until c prime. So I would have a second counter with initial value and increment value and a second condition for termination. And then I would have a nested iteration of the loop where this counter gets increased until this c prime condition is satisfied. Personally, I think that's a really terrible way to write nested loops because it's hard to read, and I strongly advise against using this. I recommend you, if you want to have nested loops, you have a separate perform statement for each of the loops. And to demonstrate this varying property of the perform statement, I will modify my collatz sequence a little bit in the way that I will count how many iterations we pass through until we reach our cycle. Let's see how we do that. First thing I do, I introduce a new variable j, which I use as a counter for my collatz loop. And then I will modify the code down here a little bit. So this check just stays the same. And now I introduce the varying clause here. So I want to use j as a counter, starting at 0. I'll increment it by 1 in each iteration. And now the termination condition is still the same. We terminate the loop once x reaches the value 1. So here indeed we have the condition that is independent of the counter. So the counter is just an auxiliary variable, if you like. And I want to modify the display, so I make it explicit which element of the sequence we're currently looking at. So xj should be the jth element of the collatz sequence equal to x. Then the test remains the same. I will just check if the current value for x is odd or even and modify it accordingly. And then in the end, I will output the final value. We can also print out how many steps we required to reach this loop, or this cycle in the collatz sequence. Okay, so I will compute the collatz sequence as before, but this time I will output the current index with the corresponding value for the sequence. And at the end, I will also print explicitly how many steps we require to get to the cycle 421. Let's clear the screen. Factorial again. Let's maybe say we compute the colored sequence for initial value 12. And this is what we get. So x0 is our initial value. And at index 9, after 9 steps, we reach the element 1. So this is where we get to our cycle. Now you could be nitpicking and say, actually, we reach this cycle in this step already, so it should be at 7 steps. But yeah, never mind. You get what I mean here. And yeah, this is a nice illustration of the varying clause for our perform statement. As another application of the varying clause in the perform statement, we could modify our code for computing the factorial of an integer number. So we could make it a bit more succinct, but this would come at the cost of introducing an additional variable for the counter. Let's see how we do that. So I introduce a different counter I here for my computation of the factorial. Of course, I could just reuse the counter for the colored sequence, but for clarity, I use two separate counters. This is the original code to compute the factorial, just for comparison. And here I have the alternative version, where I will use a counter instead of just saying perform n times. Now, just as in the first version, I have to initialize the variable fac. I do the test after. What I do is I vary I, my counter I, by 1 in each loop, starting at 1. And I will end once I reach the value n, whose factorial I want to compute. And now I simply have to write fac is fac times I, and that's it. It's not a huge difference, but it's maybe a tiny little bit clearer to do it like this. But of course you have to type more here, and you need the additional variable I. Let's try this out. So we should have the same output twice, once for our first loop that computes the factorial, and now for our second loop that computes the factorial. So this is the first one. Now the second one, well, they both compute the same thing, and that's good. They should. So you see, using this version of perform can maybe in some cases make the body of your loop easier, but it comes at the cost of having the additional variable. And it might be a bit of a nuisance if you have to declare a numerical data item just to have a counter for your loop, such as the j or the I we had in the previous example. And indeed, COBOL provides you with a generic counter variable, so one that you do not have to define, that is automatically available if you have a varying until statement in perform. And this counter variable is called tally. So instead of using j or I in one of the previous examples, we could have just used the variable called tally. So you would write it in a way, perform varying tally from something by something else until the end condition. And you can use tally like a regular data item within the loop, and outside the loop tally is undefined. But if you have multiple nested loops, then tally can only refer to one of them. So yeah, maybe don't use it if you use nested loops that all have a varying counter variable. But if you just have a simple loop where you need one counter, then tally can be quite convenient, and it saves you the definition of one variable. If you want to leave a loop early for whatever reasons, you can do so by using the instruction exit perform. So this will move you to the code just after the perform loop, so the code that comes after the end perform statement. And a variation of that is exit perform cycle, which does not make you exit the whole loop, but just skips to the next iteration of the cycle. That can also be quite helpful in some situations. Next, we're going to look at procedure calls in COBOL, which is one of the most important parts of control flow. You know what I'm talking about: procedures, functions, methods, subroutines, subprograms, basically all the same things, up to maybe some small differences in the definitions, and COBOL has them too. What they do is you interrupt the linear execution of the program flow and branch to a different part of the program and eventually return to the original position where the interruption occurred. In COBOL, you can do this in two ways. Firstly, you can do what I will call procedure calls using the perform statement, so the same statement we used for loops. And in this case, you simply jump to a section or a paragraph within your program, and you have no provision to pass parameters or return results. You just continue execution of the program at a different position and eventually return to where you made the call. The other, somewhat more involved version are subprogram calls. So these are more similar to the usual function calls you know from other programming languages. You can pass parameters here and you can return results. But what this requires is that your subprogram has to be a fully written COBOL program contained in a separate file, and then you link those files together with the main program. So you do not simply write a subprogram within your main COBOL program. And there's also the famous, or rather infamous, goto. Before we look at these in more detail, let me quickly recall sections and paragraphs in COBOL. So procedure calls via perform use the section and paragraph names in the procedure division. And we already discussed those in chapter 1, but I quickly want to recall how to use them here. Sections are defined by writing an arbitrary name for the sections beginning in area 1, so that's column 8 of your source code, followed by the keyword section and ended by a period. And paragraphs are defined by writing an arbitrary name also beginning in area 1, ended by a period. But here's no additional keyword required, so there's no paragraph keyword or something like that. And paragraphs can exist independently of any sections if you define them before you define any section in your program. But otherwise, paragraphs are used to further subdivide sections into smaller logical blocks. How helpful that is maybe a matter of taste, depends on your program design. In the following, I will use the term label when I refer to either a paragraph or a section name. So when I don't distinguish between the two, or it could be either one of them, I will simply speak of a label. First, let's look at the goto statement. So this is the simplest way to branch to a different part of the program. you use it in combination with the label, and basically what it does is you write go to label name, and then the code will simply continue execution at the position where this label is in your source code. You can use it with multiple labels and then follow it up by a depending on X clause, and X is some numerical value, some numerical variable that simply determines which one of the labels you pick for the branch. So there is sort of a conditional go to here. You can change the value of X to branch to a different label. As you may have heard, using go-tos is generally considered to be bad programming style because this leads to convoluted code that is hard to read and hard to use for your fellow programmers, and probably at some point even to yourself. Usually this is known as spaghetti code, so you should not use it. But still, for completeness, let's look at an example in COBOL. So here I just have 4 labels. I let the user enter a number and then have this go to label 1 to label 4 depending on the number entered. Here, this display wrong, this is the default code that would be executed if none of the labels was matched. So for example, if I enter a number here that is larger than 4, then I wouldn't have a corresponding label, so I wouldn't jump anywhere. And then the code would just continue executing linearly after this go to statement. So we wouldn't go anywhere. So here's my go to program in the editor. What I will do is I add another go to here. So if we do not have a suitable number for the labels here, I will print out this error message, but then I will take another go to back to the beginning of my code. So in that way I realize a loop using go-tos and a label that will continue until I enter a suitable number to go to one of these labels down here. Then I just will display the number of the label and the program will end. Let's see this in action. Enter number, so let's enter 6. We do not have 6 labels, so this should give an error. Yeah, and we did jump back to the beginning, and again I am asked to enter a number. Let's put in 3, that's a valid label. Yeah, what we do, we jump to label 3. Here we skip this part of the code, then we display 3, and because it's just a go-to and there's no provision to return to from where we called it, we simply continue executing the code from down here. So we display 3 and we display 4. And for example, if I jump to label 1, I display all 4 numbers. More interesting than goto is perform as a procedure call, and you recall we just used it for loops in COBOL, but we can also use it for procedure calls. And in the simplest form of such a procedure call, you simply have perform label name, so either a paragraph or a section name. If label name is a section, then the program continues at this section until the end of the section is reached, which is indicated by the next section header. Or if the program just comes to an end, if you reach the end of your program code. And then you will return to the position from where you called your procedure. So you will continue at the next instruction after your perform statement. And note that if your section is further subdivided into paragraphs, then all the paragraphs within that section will be executed if you call perform on a section name. And if you call perform on a paragraph name, so if label name is the name of a paragraph, then the program continues at this paragraph, so the code following this paragraph name, until the end of the paragraph. So that's the beginning of the next paragraph or the beginning of the next section. If this paragraph is contained in a section and there are multiple paragraphs within that section, then you will, in this case, not continue until the end of the surrounding section. You will just continue until the end of that particular paragraph for which you called perform. And then, as in the previous case, once you're done with this paragraph, you return to the position after the perform statement from where you did the call. Now let's see a very simple example for this. In this program, I have one variable keystroke, which I will only use to wait for a keystroke done by the user. And what I want to do is I want to wait for the user to hit a key, and then I want to perform some procedure. So in order to have a procedure, I actually need to define a paragraph, and I will do that after the stop run statement. I will just call this lonely paragraph because it's not contained in any section, and it should be here. So the label names should be in column 8, area 1. And then I will just display a message from this paragraph. Use the paragraph sign to indicate that we are within a paragraph. Let's capitalize the name. Okay, so what we expect here. What we do here is first I have to hit the enter key, and then we have performed lonely paragraph, so we will continue down here, and then we will display this message and then simply continue here in our normal code, and the program will stop. And maybe what I do is I'll display a message here where I simply state that the procedure calls are done. So you will see that once we see this message that we have actually returned to the main part of our program. And the usual error we get from GNU COBOL, you have to have a new line at the end. So now we're good. Hit enter, and you see we get these two displays in reverse order. So first we go to lonely paragraph, we perform this paragraph, printing out this string here, and then we return and print out this one here. This is a regular part of the code. The only reason I don't run into this paragraph after the perform again is because there's a stop run here. Now look at this. If I comment out stop run, then I should have one down here, but COBOL will forgive me if I don't. And then I compile this and run this again. I will get this message here twice. First when I call lonely paragraph, and then when I return, I first display this one, and then I will continue the code down here and again display this message here. Let's verify that this is indeed what happens. Yeah, you see what happens. We first execute lonely paragraph via perform, then we continue after perform with this, and because we do not stop the run here, we again run into the lonely paragraph and print this twice, as you can see here. So that's something you should be aware of when you design code with perform statements. You can also execute multiple sections or paragraphs, and for that you can use the statement perform first label name through last label name. And this will execute all sections and paragraphs between this one and that one, including the first and the last one. And you cannot mix paragraph and section names here. So if this is a paragraph name, this has to be 1, 2, and if this is a section name, then this has to be a section name 2. One important thing is, if you use paragraph names, for example, then all the paragraphs, the first to the last one, have to be contained in the same section. You cannot cross section boundaries. One issue with perform is that makes it, I would say, inferior to a regular procedure call in other languages, is that you cannot pass any arguments to the procedure. And you can also not explicitly receive a return value from the procedure. So as usual in COBOL, you have to use global variables to do that. So you have to know which variables will be used by the procedure and where any results from any computations will be written. If you want to end the execution of a procedure before reaching the end of the paragraph, then you can use the exit instruction. If you call perform on a section name, then you would use exit section to leave the procedure, and you would return to the position just after the perform statement that you use to call your procedure. So this is in that sense similar to a return statement in C, but with the difference that you cannot return any value back to the main program. In a paragraph, you could use exit paragraph to prematurely end execution in this paragraph. And what happens then depends a bit on how you called the paragraph. If perform was called on a section containing this particular paragraph that you want to exit from, then the execution will continue with the next paragraph within that section that you originally called perform on. If you used perform to call it on a range of paragraphs using the through clause that I just a few seconds ago introduced, then the execution will continue with the next paragraph within that range. And otherwise, if you simply called perform on a simple paragraph, then you would return to the position after the perform statement that you used for your call originally. Now note that, as I showed you in the simple example program before, all the code for the sections and paragraphs that will be used as procedures is contained in the same procedure division, namely that of our total COBOL program. So eventually the program flow will reach the code for these procedures regardless of whether they are called by a perform or not, unless you precede them by a stop run instruction and prevent that from happening, just like I showed you in the little example before. And we will see a few more and more complex examples in a few moments, but first I want to give you some very subjective advice on how to structure your programs. As you realize by now, perform gives you a lot of flexibility in structuring your procedure calls due to our ability to use them with different combinations of sections and paragraphs, and we can even further combine the perform procedure call with the loop properties of perform, so we can combine the perform label name with times and until. So we call a procedure a certain number of times or until some condition is satisfied. Yeah, with great power comes great responsibility. So if you use this flexibility in all its glory, then you are at risk of writing overly convoluted and hard to understand programs and thereby turning your perform statement into a go-to on crack. So something that will make your code even more unreadable than using go-tos would. So here my personal recommendations on how to structure your source code when you use procedures with the perform statement. Firstly, begin the procedure division with the main body of the program, which initializes variables and handles the procedure calls. So similar to a main function in C or Java or C# or pretty much any other modern programming language. Then I recommend you place sections and paragraphs that define the procedures below the main part of the program, so below this part here. And then you end the main part with the stop run instructions, so you avoid running into the procedures without controlling it with a proper perform call. I recommend you do not structure your programs to excess. So by that I mean avoid using sections and paragraphs within those sections. And I actually would just stick to using paragraphs. So I don't think it is ever strictly necessary to have sections and then paragraphs within those. And paragraphs without the section keyword are just easier to read. So I would just stick to paragraphs. And also, well, you might or might not agree with the sensibility of this, but I think it's a good idea to end every paragraph that you use for a procedure, say it's called my procedure, with a second paragraph name, which has the same name but prefixed by end. So the paragraph which you want to use as a procedure, that's called my procedure. At its end will be followed by another paragraph called end my procedure. And this end paragraph should contain only the exit paragraph instruction. So in this way, you can guarantee a clean return from the procedure call. Now, usually you should return by the time you reach this other label in the paragraph, but I think for readability and just to be on the safe side, it can't hurt to have this end paragraph following the my procedure paragraph. So here, this is a schematic view on how I imagine that to look. Here's your procedure division. First comes the main part. So this is where you do some stuff, initialize your variables, and from here you call your procedures. So I have two paragraphs down here that define a procedure. So my first procedure and my second procedure, and they're called in these two places here in the main part of the program. And you do something in those procedures and you end each one of them by the end my first procedure or the end my second procedure paragraph with the explicit exit statement. Of course, it's possible that you want to call a procedure from within another procedure, then you would have to have a perform statement in here, but you will know when you have to use that. So this is how I would recommend structuring your programs. Of course, for your purposes, you might have different ideas, or sometimes it might be required that you do it differently. That's of course fine too. Now let's look at some more complicated examples for the perform statement. So here I already copied in all the code I want to use because it's quite a bit and I don't want to make this too long. I begin with calling my lonely paragraph again, like I did before. And here I have a few more involved perform statements. But maybe let's look at the paragraphs and the sections first before we try to understand what's happening here. Here's my stop run. So this is the end of the main part. And down here I have a collection of my paragraphs. Now I omitted the exit or the end parts just to not make it too long, but also I want to show what happens when you run through several paragraphs. So here's our lonely paragraph that we had in the first simple example. And now I have a section here. Display starting in the first section. So I indicate the sections with an S here. And this section contains paragraphs. So I label the paragraphs by section number first and then the paragraph within that section. So I have 3 paragraphs, 1.1, 1.2 and 1.3 within the first section. And then I have a second section which also contains 3 paragraphs here. Now they all display a message that identify themselves, so you can see in which paragraph you're executing. And here in paragraph 1.2 I have an exit paragraph before displaying this message. So what we expect to happen if we get into this paragraph, that we do not see this message. And depending on how we call it, either we return to the main program or we continue with the next paragraph. So let's see in a moment how we can do that. And here in paragraph 2.2 I have an exit section. So whenever I get into this second procedure section here, I expect to leave it in this paragraph. So I should never reach paragraph 2.3 if I begin in this section here. And we can try this out in several different ways. So first we call our lonely paragraph. We've seen that before. Now I combine the perform statement for the procedure call with the perform statement for the loop. So I will perform lonely paragraph 10 times. So we'll loop over the procedure lonely paragraph 10 times. So we will see the display from this paragraph 10 times. Then I will simply call paragraph 1.1, this one here, and we will see that the only output we get will be this line here. So because I use perform in the paragraph name, we will not continue with the following paragraphs. Then I will call perform paragraph 1.1 to 1.3. So I will use the through statement for that. So I expect to execute these 3 paragraphs here. But what I expect is that I will not see this string because the exit paragraph will leave this second paragraph before I reach it. And with a through statement, I expect to continue in this one. So I will, in this case, I expect to see this and this string. Here in the comments, you can see I have an invalid statement where I combine the perform statement, perform paragraph 1.1 through paragraph 2.2. So here I use paragraphs in 2 different sections, and that is not allowed. So I can show you how this gets you an error when you uncomment it. Otherwise, I will just call perform on a section. So I will perform first procedure section. And that means I will start here and go through all the paragraphs contained within this section here until I reach the next section, which would be here. So I expect to see everything here except for this one again because of the exit paragraph. And then I will call perform with a through statement for 2 sections. So that there I expect that I will execute both the first and the second section. So all of these paragraphs, well, up until here, because here's exit section. So I expect the execution to end before I reach this last paragraph. Okay, that's a lot. Now let's do this step by step. First I compile again, no errors, that's quite lucky. We have a keystroke before every perform, so we can do it slowly. The first thing is perform lonely paragraph. And indeed we get the output from lonely paragraph. Now we do lonely paragraph 10 times. So I want to see this 10 times. Great, that works. Now we perform paragraph 1.1. So I only expect to see this message here. So far so good. And now we perform 1.1 through 1.3. So these 3, but because of this exit paragraph, I expect only to see this and this string. And indeed, we skipped this one because of the exit paragraph. Next, we have, well, this is not active now, so we will call the first procedure section. So I will expect this message with this one and that one. Indeed, that worked. And finally, I will call first procedure section through second procedure section. So everything from here to here, and because of this exit section, this one should be omitted, and also because of exit paragraph, that one should be omitted. Let's see, yeah, we do not have 1.2, and indeed we end after 2.2, so we don't reach this point. And then we get the message from the main program that we're done. So this all works like we expected, and now I will just show you the error we get here. Yeah, so even the compiler complains that the paragraph 1.1 and paragraph 2.2 are not in the same section. So this is something you cannot do. Perform from one paragraph through another that are contained in different sections. So let's comment this out again. What we can try is, I will uncomment the stop run here, so we will again run into all of these paragraphs and sections just by naturally continuing after the procedure calls in the main part. And there's an interesting thing here that in theory, if you run into paragraphs or sections just linearly, not by calling them with perform, then COBOL actually says that the exits should be ignored. But in fact, GNU COBOL will not ignore them, as we will see. So we will get exactly the same output at the very end as the one we got with this perform here. At least that's what it was like the last time I tested it. This was the call from section 1 to section 2. Then we were done with the codes, and here you see we just execute all of the paragraphs again because we do not stop running here but just continue. So we start with our lonely paragraph, first section, second section, and the exits are not ignored in this case. So yeah, maybe in that sense GNU COBOL is a bit off the standards, or maybe different COBOL standards have different requirements for that. But these exits always are effective, no matter whether you explicitly call the section or paragraph or whether you just run into it by naturally running through your program top to bottom. Let us now come to the other way of calling procedures in COBOL. And this is for so-called external procedures or subprograms. Now these can be written in COBOL or in a different programming language, and they must be linked together with the main program on compilation. I will first explain how to use such subprograms, and then in a few minutes I will actually tell you how to write them and link them, and then we will look at examples. So here, that's the simplest form of how such a subprogram call would look like. You use the instruction call with the name of your subprogram using by content argument 1, by content argument 2, by reference argument 3, returning ret val. Now you can maybe imagine what these parts are, but let's go through it one by one. The call instruction is actually that which invokes your subprogram, and you have two ways of doing that. First is the static call, which you see here, where you give the subprogram's name as a string in quotation marks. So that's important that you really put it in quotation marks. The other way to do it is a so-called dynamic call. And here you give an alphanumerical variable to the call that contains the name of the subprogram as a string. So that's why it's called dynamic. You can actually change the name of the program at runtime, and then depending on what your program did before, maybe call a different subprogram. You can pass parameters to subprograms with the keyword using. So this means your subprogram uses the following parameters. And then you have these optional modifiers here, they can be omitted, which determine how you pass the data to your subprogram. I will talk about those in a minute. And then you have the also optional keyword returning, which indicates a variable that should contain the return value from the subprogram. First, let's have a look on how parameters are passed to the subprogram. So this is the example I'm using. Call my subprogram using by reference x. So this means my subprogram expects one argument, one parameter, and we give this in the variable x. And we want to pass it by reference, as we say here. So what's the setup? Let's say we have three variables, x, y, z, that are located somewhere in memory, and here these are the addresses in memory. Of course, these are just made up. Normally the addresses would be on a much larger scale, but just for the sake of examples. And if I do a call by reference, so using the by reference modifier here, then what I will actually pass to the subprogram as the first argument is the address of the variable x, not the value that x contains, not the value that is in memory here, but the address of this piece of memory. Now it's important to understand that COBOL does not know pointers. So even though we give the address of the variable x to the subprogram, if we refer to argument 1, then COBOL will automatically dereference it, and we will get the value of x of the variable, so the value that's in this location of memory. We have no access to the memory address directly. What this means, of course, is if we pass it by reference and the subprogram modifies the data at this address that it's given here, that if we make any changes to x and we return to the main program once the subprogram is done, then the changes will persist in memory because the main program looks at the same part of memory when it references x. So this is a way to pass a variable to a subprogram where you want the changes to persist. And this is actually one possibility to return values from the subprogram to the main program. So that's important to understand. The second way of passing arguments to a subprogram is this one, call my subprogram using by content y. So this may be a bit odd. It's similar to the by reference, but what happens here is now we want to pass the parameter y to the subprogram. We first create a copy of y somewhere else in memory, and then this copy is passed by reference to the subprogram. So we will actually take the address of that copy and pass that to the subprogram. And that way we only have to pass the address, not maybe the whole value, not all the data that is contained in y, which could be much greater in size than just a simple address. But if we modify the argument 1 in the subprogram, then the changes will be written to this memory address here, and our original y will be unaffected by that. So that way we can pass parameters to a subprogram that, even if they are changed, will not affect the value in the main program. Finally, we have the call by value. This will directly pass the value of the variable to the subprogram. So here's the example, call my C subprogram using by value z, and note the C here. Here we have z as the argument, and what will happen is we will take the value of z directly and hand that to the subprogram. This is used for compatibility with subprograms written in other languages, such as C. That's why I call it my C subprogram. And it should not be used for COBOL subprograms. Of course, here, if we pass z, the value of z to the subprogram, then this will be in a different memory location, the one that was reserved for the argument, and therefore changes made to z or to arg1 in the subprogram will not affect the value of z in the main program. Also, we can return values from a subprogram call using the returning keyword. It looks like this, call my subprogram using whatever arguments we have with whatever calling procedure. And then finally we can write returning r, where r is some data item that has to be of the appropriate type for whatever type of data is returned by my subprogram. The return value is passed by value to r, so it will be copied into the variable r. This means returning a larger data structure would require copying a larger amount of data. So that's why it might be more efficient to pass an argument by reference to the subprogram and just modify this argument within the subprogram, and then the changes will be seen in the main program if you have a larger data structure that needs to be returned from the subprogram. One interesting thing about this returning is that IBM COBOL provides a system variable called return code that can be used instead of this R here to contain the return value. And this would simply save us defining a variable particularly for this purpose. And on IBM hardware, there's actually a special register reserved to hold the return code. The dynamic call, as I said in the beginning, is the call where you use an alphanumerical variable holding the subprogram's name and then using arguments, maybe returning a value just like in the static call. But here we have to take a few things into account. First, when we have this kind of call, we need to make sure that the arguments we write into the using clause here match whatever function name is stored in this variable here. So we should not put a function name or a subprogram name in here that has a different number of parameters as the ones that we list in the using clause here. Now, one problem is again with how COBOL handles strings. So this will be an alphanumerical variable that is defined to be of a certain length. Now let's say it's n characters. If the name of the subprogram that we put into that variable and then want to call is less than n characters long, then this variable will be filled up with blanks up to its prescribed length. So the missing characters within those n characters will be blanks. But by filling it up with blanks, this augmented string is actually no longer identical with the original subprogram's name. And so call will not identify it correctly. So what we do is we use our trim function again to remove the trailing blanks. So instead of just putting sub here, we should have call function trim sub trailing. So that way we remove the blanks and the subprogram name will be identified correctly. And there's also the possibility to have some exception handling for the call instruction. For example, if we put in a subprogram name that doesn't exist or we use the wrong number of arguments. And this works as follows: call and then whatever parameters we have for the call instruction, and then at the end we write on exception C, where C is the piece of code that will be executed if some exception occurs. And we will look at examples for subprograms in a few minutes, but first I want to show you how to write subprograms now that you understood how to call them. And a COBOL subprogram is written in almost the same way as a regular COBOL program is, but with some important changes or additions. First of all, the arguments for the subprogram and the variable holding the return value must be defined in the linkage section of the data division and not in the working storage section. So that is what linkage means. This is the part where the linking of the two programs takes place. The arguments that are handed from the main program and the return value that is handed back to the main program. Any other variables or data structures that you will use in the subprogram, but not necessarily hand back to the main program or take as arguments from the main program, can be defined in the local storage section, and they should be defined there ideally, rather than in the working storage section. Now, what does the local storage section do? The difference between local and working storage section is that the memory for the local storage section will be allocated dynamically on the subprogram call, and it will be freed once the subprogram returns to the main program. The procedure division of the subprogram must list the subprogram's arguments and the variable holding the return value in its header. So this would look like this: procedure division using arg1, arg2, blah, blah, and any other arguments, finally returning R. So R would be the variable holding the return value. There's no explicit return statement for subprograms, so the return value R will be whatever value R has when the subprogram ends and returns to the calling program. Now here's a bit of a tricky issue. At this moment, GNU COBOL does not support using the returning keyword in subprograms. So if you want to practice subprograms in GNU COBOL, you cannot use this. However, you can use returning in subprogram calls when you call C functions as subprograms. And I will talk about this a little bit more in an upcoming chapter on modularization. So be aware of this. You cannot use returning when you write your own COBOL subprograms. And if you want to compile and link a program and a subprogram with GNU COBOL, you have to use the following command. copc for a compiler, -x to create an executable, standard equal to IBM, main program cop, so the source code for the main program, subprogram.cop in a different file, the subprogram. And now you have to explicitly state the name of the executable you want to create by -o and the file name of the executable. So yeah, usually this will be the same as the name of the main program. But if you have multiple parts of the program, multiple files, you have to explicitly state the name of the executable. How to return from a subprogram? So I just said we don't have an explicit return statement for subprograms. So by that I meant we don't have a return statement that hands back a return value, but we do have instructions that can end explicitly the execution of a subprogram. And normally the subprogram ends when you just reach the end of the code, but you can force the return to the calling program with exit program or go back. So either of these instructions does that. You can also call stop run from a subprogram, but this will not return you to the calling program, but it will terminate the main program as well. So this is like an exit 0 in C. You will be returned to the operating system if you call that. IBM's COBOL standard officially requires you to end your subprograms with a marker and program my subprogram or whatever the name of your subprogram is. But if you try this out in GNU COBOL, or if you leave it out in GNU COBOL, you will see that GNU COBOL doesn't care too much about that. So you're not forced to have this in your subprograms by GNU COBOL, but of course I will have it in there anyway for compatibility and just in case you want to use the code on some other platform. Now let's see some examples of subprogram calls. Here's my program to test the subprogram calls. A very simple form, similar to the one with the procedure calls with perform. I wait for a keystroke and then I call a subprogram named sub_program. And here I use the onException, the exception handler, and if something goes wrong, if I don't find this subprogram, then I will just display subprogram not found. Alternatively, in a more serious program, I could branch to some error handling part of the code, but here this is good enough. Now, let's compile this, same file name as before, and call it. And indeed, we get an error. Why is that? Well, as you can see here, I did not include any subprogram file that I would link into my executable. So, of course, I don't know any subprogram called sub_program. Here I've created one, and we see a little COBOL subprogram and the format for that. So I ended with nprogram subprogram. Identification division is just like in a normal COBOL program. In the data division I have the local storage section, but yeah, I don't actually use this variable for anything. And I simply display a greeting message from the subprogram. Let's compile this in the proper way. This is all correct, and also I need to have my main COBOL program, but now I need to include the name of the subprogram and explicitly state the executable file's name. And I get an error. Of course I do. Why would I not get an error? This error is because I have my ends program in the wrong column. This has to be in column 8 and I had it in column 7, probably because I removed the comment sign before. Now it works. We will run it, and I hope this time I will not get this error, but I would rather call the subprogram and get this greeting here. Yeah, this is what I hope to see, and this is what I do see. And after the call, I return to the main program and I see the confirmation that I'm back in the main program. So that's all good. And now I want to actually do a dynamic subprogram call. So I will ask the user to enter the name of the subprogram I want to call. Display and I will just use the variable keystroke again for that, but now I will actually read the value of a procedure. And then I will call keystroke and I also want to have an exception handler for that. So here we will get an exception if we call a subprogram that doesn't exist. Now let's see how that goes. And I will include a second subprogram, so I have some choice, and this I will just call DOM program, and it looks exactly like the other subprogram, but just so that I have a different name. I have to include it in the list of my programs. Okay, so here we just get the greetings from the first call here. And now I can enter the name for a dynamic subprogram call. Let's just call this one here again. So I enter subprogram. And I get a greeting from the subprogram. I'll be honest, I didn't expect that. I was expecting to get an error because I would have thought that I would first have to trim this from its trailing blanks, but apparently this worked. Now let's try it with DOM program. And here we get a different message. We get greetings from the DOM program. So that means we actually called this one here. Now I just enter some garbage and we get our exception here. So what I mentioned before, I thought I would have had to use the trim function like I used so many times before, and I'm somewhat pleasantly surprised that this actually worked. I can also do it like that. That should not cause an error. Yeah, but you don't have to. So just writing it like this also does the job. So what we've seen, a subprogram call in the static way where we hardcode the name of the subprogram, and then the dynamic subprogram call where we can actually change the name of the subprogram we want to call, and according to that call different subprograms. An interesting question on COBOL subprograms is actually if we can write recursive subprograms. So procedures that call themselves or that call other procedures that call the original one. And traditionally COBOL did not allow us to do this. But the more modern COBOL standards provide the possibility to do this, and you can do it by explicitly declaring your subprogram to be recursive. You have to do this in the program's name and the program ID. So you just write program ID and then the name of the subprogram, And then after that, you write the keyword recursive. You have to call a recursive subprogram from a non-recursive main program first. IBM COBOL is sufficiently modern to support this, and the GNU COBOL compiler also supports it. So I want to give you a little demonstration of a recursive subprogram call in COBOL. And I will do this by this example by computing the Fibonacci number, the nth Fibonacci number, Fn, where n is some positive integer. And you may or may not recall that Fibonacci numbers are defined by the following recursive formula. So the first and the second Fibonacci number are both defined to be 1. And then we say that the nth Fibonacci number is defined to be the sum of the two preceding ones from index 3 onward. And here we have a nice recursive definition, so we can put this into code and we will see how COBOL handles recursion. As I just said, we have to call a recursive subprogram from a non-recursive main program. So this is my main program called Fibonacci. As you can see, I have two variables here, n for the index of the Fibonacci number, and Fn, which should actually hold the value of the nth Fibonacci number. And here I let the user enter a positive integer. I'm not going to check if it's really positive, but actually this data format here doesn't allow negative numbers. And then I call a subprogram, a recursive subprogram called Fibo_rec using n and Fn as parameters. I copy n by content, so I don't want changes made to n in the recursive subprogram to reflect the value in the calling subprogram. That's important, otherwise I would completely screw up the recursion. And by reference, I pass Fn because I want Fn to actually hold the result at the end of computation of Fibo_rec. And then in the end, I will just display the value for the nth Fibonacci numbers. So it's important to see how I implement this recursive function. I have this here. Identification division. We start with the program ID. Usually this is not a very spectacular thing. Of course, it has to have the same name as I call from the main program. And now you see I have to explicitly declare it as recursive by putting the keyword recursive here. In the data division, I first define the local storage section. So remember, I do not want to use the working storage section because that one would persist in memory. And the local storage one is allocated and freed up dynamically, so that's a bit better. Since I have to use two preceding values to compute the nth Fibonacci number, I define two indices as binaries, so n1 and n2, which will actually hold the values n-1 and n-2. Then I define the two preceding Fibonacci numbers. And now I need to make space for the arguments used by the subprogram, and for this I use the linkage section. And it's important to notice the linkage section has to come after the local storage section or the working storage section if you use that one. Otherwise you'll get an error. Here we have n as our first argument, which is a 2-digit number, binary type, and we have Fn, which we take a 10-digit number because Fibonacci numbers can grow quite large rather quickly. And here we have the procedure division, and we need to declare n and fn as our arguments here with the using clause. And finally we end this recursive subprogram with end program. Now we can actually write it. So first we need to check the case that we have one of the first two Fibonacci numbers. So if n equal to 1 or n equal to 2, then we do not have to get into the recursion. We will simply, oops, this is wrong, this should be here, and in that case we will just move the number 1 to our Fibonacci number, and we go back from our subprogram. If we do not have one of the first two Fibonacci numbers, then we have to use the recursive formula to compute it. So first we set n1 to n minus 1. Recall I have to use the spaces here, otherwise n-1 would be considered to be a variable name. And we set n2 to n minus 2. And now we recursively call fiborec using by content n1. So we compute the n minus first Fibonacci number and store this in fn1. And we call fiborec again to compute the n minus second Fibonacci number. And once we're done with that, so after these two recursive calls, we should have the value of the n minus first Fibonacci number stored in fn1 and the value of the n minus second Fibonacci number stored in fn2. And then we can compute the value of the nth Fibonacci number by simply adding those two. And then the subprogram ends, and because this is the value stored in fn at the end, this will be what we return to the main program. Now let's compile this and see how it works. These are the two programs we compile and link together, and the output should also just be called Fibonacci. And we have a syntax error, of course. Yes, I'm not allowed to use periods in the if statement. Silly me, how could I have possibly forgotten that? Okay, let's see. Let's maybe try the first Fibonacci number first. Yeah, and we just run into this condition here. We do not do any recursion. We just hand back the value 1. And let's maybe use the 12th Fibonacci number. We get 144. I hope that is correct. You can probably Google this. What is the 12th Fibonacci number? So up to this point we've learned quite a bit about how to control the flow of a COBOL program, and we can actually do a lot of interesting things now. So I want to show you a more complex example where I want to pretty print a matrix of arbitrary dimension to the terminal. You may recall from chapter 2 that we could do some moderate formatting of data by using filler items in the definition of a record, but there were limitations to that because of the way COBOL stores the data, and especially you could not really use this well with records or tables of variable length. So it's better to use procedures or subprograms for that, and this is what I want to do in this matrix printing example. But because this video is long enough as it is, I will not do this right now, but I will record a separate video for that. And this will be called a B-side to the current chapter of my COBOL course. And in this example, I will use subprogram calls, I will use conditions, I will use loops. So everything we've learned so far will be applied in this example. And I think it's quite nice to do this, and also quite interesting to see how to print a matrix on a terminal screen. Look out for my video on this. And now we continue with some built-in sorting and searching functionalities of COBOL. We will now have a look at COBOL's built-in searching functionality. Obviously, searching through data sets for a particular item is an important task on any computer, and in COBOL you can organize your data sets in tables, and COBOL offers some built-in methods for searching through these tables. There are two ways of doing this. So say we're looking for an item X in a table T that has n entries, then the generic way for arbitrary tables T is to search linearly through them. That is, you start at the first entry and go to the next and the next after that until you reach the last one, comparing each one if you find the item X. And as the name linear search suggests, this can be done with linear computational effort, O of n. Then there's a special case when you have a table that is already ordered. So the elements can be sorted in some way, and you assume they already are in your table. So in this case, you can use the so-called binary search, which is basically the way you look up a name in a phone book. So you open the book in the middle, and then you see the name you're looking for, is it on the left or the right, and then you just continue in that half that you know the value you're looking for has to be in. So in every step you halve the size of the data you have to search through, and in doing so you can find the element X you're looking for with logarithmic computational effort, O of log n. But of course this only works if your table is sorted to begin with. And of course we also need to have some procedure that handles the case that we do not find the element X in our table T. The built-in function to search tables is called search, naturally. This assumes you have a table with one index variable. Recall from the previous chapter where we introduced index variables. These are special variables that only serve the purpose of indexing the elements in a table. You have to define one for your table to use the search instruction, and here's an example of how that would work. So in the data division, working storage section, we define our table. So I call this the Simpsons because I use the Simpsons names again as an example. And just as for the sake of illustration, two entries, first name and the age. Then here I have a variable S name for search name. This I will use to hold the value that I'm looking for. And in the procedure division, I assume that in the previous code I somehow picked a name that I assigned to S name that I want to search for. And then I write search table name, Simpsons in this case. At end display is the message I print if I do not find the element. This is an optional item in the search command. And here the when clause is what I actually use to search for the given name. So when the given name equals first name index. And index is the index variable that we define for our table, and search will automatically iterate over this index variable. So it will automatically increase it one by one in each round of the search until we have iterated over the whole table. And if we have satisfied this condition that the search for name equals the first name for a certain index, then we print out the message of success. So in this case, we just print the name, the position at which we found it, and then Also, why not the age of the Simpson character and this index. And as I said, the @n clause handles the case when the search for item is not found. And we can use more than one when clause in this search. So we could formulate different search goals that all have to be checked. And if one of these conditions is met, then the search ends. It's also possible to use a different index variable than the one defined in your table, say index 2. And then you would have to supply your search instruction with the clause varying index name of that other index. Okay, let's look at this example in practice. Here I have some code to move some data to populate the table. So this is not really that interesting, but it's just Homer, Marge, Bart, Lisa and Maggie, and I move those to the respective entries with their respective ages. And then I ask the user to enter a search name, which I read in here, and now I have to actually search for that. First I have to set the index for my table to 1, so I actually start at the beginning. If I only wanted to search part of the table, I could set the index to a different value, but now that doesn't make sense, so I'll search the Simpsons table. In case I do not find what I'm looking for, I will output that I did not find it. Again, no periods allowed while the search statement is active. My first when condition, so when the S name equals the first name in the table at the current index. And then I display my message of success. And I just output the age. No periods here. And I end the search with the end search. Now let's try this out. I'll enter a name, let's say Maggie. We should find that one. It is contained in the table. Yeah, found Maggie at entry 5. That's what we would expect. And the age is 1. Right. Let's try it again with a name that's not in the list. Let's say Ned. And we get this displayed here. We did not find Ned in the table, so we get the Ned not found string. Now, of course, it's also possible to write a loop using the perform instruction to search through a table. And in fact, if you want to search in a table that is indexed by 2 or more indices, then you have to use perform, because unfortunately search simply cannot do this. You can't have 2 nested search instructions that search through a table with 2 or more indices. And just a few words on the binary search. The binary search in COBOL can be done using the search all instruction. So very similar, but the keyword all is important here. And this can only be applied to tables that are declared to be sorted. How do we do that? Of course, we do this in the declaration of the table in the data division. And we have to use one of the clauses, ascending key is X or descending key is X, where X is some attribute of the table. And the data type of this key can be any display type. So alphanumerical, binary or packed decimal. And here it's just a quick example that you can try it yourself. Here we sort the Simpsons, or we assume the Simpsons table is sorted by age. So I call this table sorted Simpsons. The declaration of the table is very similar to before, but here I have ascending key is age, indexed by our index variable. So this part is new, where I declare that I assume that this table is sorted in an ascending order, so from youngest to oldest with regards to the age entry. In the procedure division, again, I assume that somehow I've been given a value of an age that I'm searching for. For example, if the user just types it in via an accept instruction. And now I have search all sorted Simpsons. Again, I have the at end if I don't find anything. And now it's the same. When this age matches the age of the current index I'm looking at, I display my success output. And this will simply run a little bit faster, or actually much faster on large data sets than the linear search will, if we assume, or if we can assume, that the table is sorted by the time we put it into the search all statement. In the final section of this chapter, we want to have a look at COBOL's built-in sorting functions. COBOL does provide a built-in sort command, which in itself is a very nice thing. But as you can imagine, knowing a little bit about COBOL now, such a nice feature comes at a price. The syntax of the sort command is quite awkward, and it's really not very intuitive to use, at least not in its more complex version. But let's see what we're dealing with here. Sort is designed originally to sort data in files. It's not designed to sort data that is contained in memory. And that makes it a bit unusual, at least if you're used to more modern programming languages. Now, we can use sort to sort data that is contained in tables, but we will require at least one file for this sorting process. This file that we require is a buffer, or you could also call it a swap file if you like. And this buffer is used by the sorting algorithm to store temporary data. Now, this may seem a bit eccentric to you, but this is actually a leftover from the olden days where random access memory was not widely available, and you could not easily spare some of it to perform sorting procedures. So this is why COBOL originally was designed in a way to use a file, an external file, as a buffer for the sorting algorithm. Now, there are two modes for this sort command in COBOL. The first one, which I call the simple mode, just directly reads data from one file for sorting and writes the sorted data to another file. And then there's a more complex mode, which allows us to pre- and post-process the data before and after sorting. And this latter mode actually allows us to sort tables in memory and not just external files. Let's look at the simple mode of sorting data first. What happens here is we provide an input file, an external file that contains the unsorted data, together with the keys by which to sort. So this file is supposed to contain some COBOL records, that each of which contains certain attributes, and we give some of these attributes as keys for the sorting algorithm to sort the data by. And this is just the usual file in COBOL that we declare with an FD file descriptor. Then the sort procedure sorts the data using another file as a buffer. And this other file actually has to be declared as SD. So this is a special file descriptor for these sorting buffer files. Finally, the sorted data is written to an output file, which again is just an ordinary COBOL file, and this may or may not coincide with the original input file. So if they coincide, then of course the original unsorted data will be overwritten. And here we have an example for the syntax of such a simple sort. So first sort, the keyword for the sorting procedure. And it's maybe a bit unusual, but we give the buffer file as the main argument to our sorting procedure, not the input file, which you might expect more naturally. Then we provide 2 keys, or we could even provide more keys if we want to, but in this example it's 2. We provide 2 keys for the sorting algorithm to sort the data by. So here I again will use some personal data with first name, last name and age. So we use age as the first key and then last name as the second key. And by stating on descending key or on ascending key, we can tell the sorting algorithm in which order they should be sorted for the particular key. So here on descending key age would mean we sort from oldest to youngest. On ascending key last name would mean we start with the letter A and end with the letter Z. Any key that we use here for sorting must be an attribute that appears in the record that is assigned to the buffer file, or the input file, or the output file. So these 3 files must have identical records assigned to them. And indeed, at least in GNU COBOL, we could pick this key from either one of the records for the buffer file, the input file, or the output file. Then we have these 2 clauses here, using and giving. Using is simply the name of the input file. So using unsorted file means the file descriptor unsorted file points to the file on disk that contains the unsorted data, and giving sorted file means sorted file is the file descriptor that points to the file on disk, which will at the end contain the sorted data. To make sense of this sorting procedure, input, output and buffer file must have identical data structures assigned to them. And I will talk more about file handling in an upcoming chapter, but just enough here to understand how the sorting algorithm works. The file descriptors for the input and output files are just ordinary COBOL file descriptors declared with FD, whereas the buffer file for the sorting algorithm must be declared using SD. So here's the full declaration of the files and their descriptors. In the input-output section, file control paragraph, we have the buffer file, the unsorted file and the sorted file, each assigned to actual files on disk. And here we declare the data sets for each of these file descriptors here. So SD is the special descriptor for the buffer file. And you can see each of these records here for each of the 3 files contains the same data structure. So let's see this in an example. First, I actually want to show you what the input file looks like. So I call it unsorted.dat for data. And it's not very nicely formatted because it just dumps the data as it is written in the file. But you can see again, I have a lot of characters from The Simpsons and I have last name, first name and age for all of them. So I have Homer, Marge, Bart, Lisa and Maggie Simpson with their respective ages. Then I have Ned and Maud Flanders, Barney Gumble and finally Mr. Burns. What I'm going to do is I am going to sort them by age, starting with the oldest. So I would expect Mr. Burns here, who is 99 years old, to be the first entry in the file rather than the last. And by the way, I just made up these ages here. I have no idea how old Mr. Burns is supposed to be in the show. So if you're a hardcore Simpsons fan and know better, then please don't get offended. And then I'm also going to sort by a second key, which is the last name in ascending order. So for example, we have Homer and Ned Flanders, both being the same age. So they will be in the same position age-wise, but because Ned Flanders' last name starts with an F and Homer starts with an S, we would expect Ned to be sorted in before Homer. So let's realize that now. This is what we saw just a moment ago. Our external files on disk defined in the environment division, input-output section, file control. Here in the data division, in the file section, I have the corresponding data structures with the file descriptors for each of these files. The buffer file, the unsorted file, and the sorted file. And yes, it is quite annoying to have to type this for each single file, even though it's the same everywhere, but that's the COBOL way. Now let's realize our sorting procedure. So we use the sort keyword, give the buffer file as the first argument, and I want to sort by age first. And just for clarity, I will use the buffer set. And then as a second key, I will use the last name in ascending order. As the input, I will use the unsorted file. So I use this file descriptor here. And for the output giving, I will use the sorted file. Period. And there's no end sort keyword, so a sort statement actually has to be ended with a period. And once we get here, I will just confirm that we reached the end of the program. And that's it. Let's try this out. The sorting is done. So remember, this was our input data here. And now we'll output the hopefully sorted data. And yes, that seems to have worked. So Mr. Burns is in first place because he's the oldest. So our first sorting key was the age in descending order. So the oldest comes first. Then we have Barney, who's 40 years old. Again, I just made that up. And then we have Ned and Homer, both of whom are 36 years old. And Ned comes before Homer because his last name, Flanders, comes before Simpson alphabetically. And we have the same for Maud Flanders and Marge Simpson. They're also of the same age. And again, Flanders comes before Simpsons. And finally, we have Bart, Lisa, and Maggie just sorted by descending age. So that worked just like we would expect it to. Now let's look at the slightly more complex version of the sort instruction. So here we can replace the using and giving clauses by some pre- and post-processing procedures. More precisely, using is replaced by input procedure I, where I is some label referring to a paragraph or a section if you prefer, containing the code for the input procedure. And giving is replaced by output procedure O, where O is a label referring to the code for the output procedure. So the little picture here shows it. Again, we read the data from an external file, the unsorted data file. Then we process it in some way, use sort together with the buffer file, hand the sorted data to another processing procedure, and finally write it to the file for the sorted data. The input procedure pre-processes the data and decides which item from the data set are handed to the sorting algorithm. And in principle, you could put arbitrary code into your input procedure. Usually you would run a perform loop that iterates over the input data and performs some modifications or checks before the data is handed to the actual sorting algorithm. And the command release dataset hence the data contained in dataset to the sorting algorithm. And here dataset must be a record of the same type as the data structure assigned to the buffer file. The output procedure will be used for post-processing the by now sorted data. Here, the command return buffer file will read the next entry from the sorted buffer file. And if you want to put it into a particular record to do some more processing with it, you can use return buffer file into dataset. And this return into instruction actually allows us to apply sort to tables rather than files by simply returning the sorted data into a table. Then there's an optional clause @end C within the return instruction that allows us to execute some command C once the last entry from the buffer file has been returned. And we can use these input and output procedures to read data that is released from a table and return the sorted data to another table. So in this way we can apply the sort instruction to tables rather than files. So it's depicted here. We have some table containing the unsorted data. The input procedure will hand it to the sorting algorithm, which still has to use the buffer file, so we can't completely go fileless. And then the sorted data will be handed to the output procedure, which will write it into a sorted table. And it's also possible to combine table and file sorting, so we can read from a file and sort into a table, or we can read from a table and sort into a file. Let's see how we can sort two tables in COBOL. Here's our program to sort tables in COBOL. In the file control paragraph, we only have the buffer file now. We do not need an input or output file, but we still need the buffer file for our sorting procedure. And here in the file section, we declare the data structure for the buffer file. Our input and output data will be taken from tables now, so they are declared in the working storage section, where we have an unsorted table for the input data and a sorted table for the output data. Now in the procedure division, I first have a lot of instructions to simply initialize the unsorted table, the input data, because we do not read it from a file this time, so at some point we have to enter it, and I didn't want to do it manually now, so I have all of this here. And here I'm just printing out the unsorted table in an unformatted way, so I'm just dumping the data just so that we can compare what the table looks like before and after sorting. Now here I will write my code to read the data from the unsorted table and then sort it. Again, I have to specify the buffer file. And I use the H as the first key for sorting. And as before, as the second key, I use the last name. And now I will not use the keywords using and giving for the input, but I will use input procedure. I will call this get unsorted. So this will be a procedure that takes the entries from the unsorted table and hands it to the sorting procedure. I have to define this down here as a paragraph with the name get unsorted. And I will of course do this after the stop run statement, so I don't run into it by accident. paragraph name first, and then I perform a loop over all the entries in the unsorted table. I use the generic counter variable tally that I told you about before as a counter, because I don't want to introduce a separate variable for that. And I will run the loop just until I reach the counter of 10. And 10 is the hard-coded size of my unsorted table. That's not a very elegant way of doing this, but for illustration purposes, this should be fine. What I will do here is I will move the current element from the unsorted table to buffer set, so to the record that is associated with my buffer file. And then I will just call release buffer set. And this hands the current data in buffer set to the sorting instruction. That's all I will do here. In principle, I would have the option to perform some processing on the data in buffer set. For example, I could run some checks, and depending on how these checks come out, maybe decide not to give this particular entry to the sorting algorithm. Or I could modify some data before handing it to the sorting algorithm. I could do this here before calling the release statement, but for this example I'm not doing anything fancy. I just take every entry from unsorted table and just hand it to the sorting algorithm. And out of principle I will use my end label here. Next, I have to define the output procedure. Since I called the input procedure get unsorted, I will call the output procedure set sorted. And this will be the last statement in my sorting instruction, so I end it with a period. Let's define the set sorted down here. So again, I run a loop. From first to last over all the sorted elements. Again, I run it until I reach the counter of 10, which is the hard-coded size of my data set. And now I use the return command, return buffer file into sorted table, so into the current entry in sorted table. So I will, in each iteration, take one entry from the buffer file and write it into the sorted table. And here's the optional at end statement, which actually is part of the return instruction. But I don't really want to do anything at the end, so I just write at end continue, or I could just leave out this statement altogether. Those are my sorting pre and post processing procedures. And the only thing I might want to do at the end is to actually display the sorted table. And that's it. Now let's test this. All right, what do we get? Here's our unsorted table, just in the order in which I entered the data at the beginning of the program here. Then I sorted first by age, and we see indeed Mr. Burns is on top again. And the second key I use for sorting is the last name. And we see again that Homer and Ned, who have the same age, are sorted alphabetically in ascending order. And one final thing I want to tell you about is the merge instruction in COBOL. This is related to sort in the way that you can take two sorted files and merge the contents of those two files into a third file or into a table. The syntax is very similar to sort, with some exceptions. Here you can provide multiple input files, not just one, via the using clause. There's no input procedure, so you cannot take input from tables and you cannot pre-process it in any way. But you can still use an output procedure if you like. And then in the giving clause, you can actually provide multiple output files, and these will all contain the same data in the end. Here's an example for that. Merge, again, the first argument is the buffer file you use. You state the keys by which you want to sort using sorted file 2 and sorted file 1. So you need to have sorted input files for that. Giving big sorted files. So this will contain the data from both of these files, but sorted together. So merged together while writing to this file. And I want to quickly show you a final code example for that. And what I will do in this example is I will create two tables with unsorted data. Then I will use sort to sort each table into a file. So I will use table to file sort. And then I will use these two sorted files to merge them into one big sorted data set in a file. I already have the complete program here, so I'm not going to type anything. Here in the environment division, we have our 4 external files, our buffer file, 2 files in which I want to sort data, so they will contain sorted data once they're written to. And then I will merge these 2 sorted files into a third file. Here are the corresponding file descriptors with their records, so they all contain the same data types. In the working storage section, I define 2 tables that originally will be unsorted. Now I initialize my first unsorted table with some Simpsons characters data, and I will initialize a second unsorted table with some other Simpsons characters. And here I use sort to sort the first table into a file. So first I will just dump the table data. Then I will set my sort index to 1 and apply the sorting procedure. Now why do I need this sort index? Because, well, what I did here is I used one input procedures for both tables, but down here I actually look at which table I'm currently handling. So if the sort index is set to 1, then I look at the first unsorted table, and if the sort index is set to 2, I look at the second unsorted table. But otherwise the only thing I do is I read the entries from the table and release it to the buffer set, so I hand it to the sorting algorithm. And this is all that happens here. I take the input from my unsorted table number 1 and write it to sorted file 1. And here I do exactly the same for the unsorted table number 2. I set the sorting index to 2, so when I call get unsorted, I will use the second table and I write this to sorted file 2. And here's the main part, the merge instructions. So merge buffer file. Here I have the keys by which I sort using the two input files, sorted file 2 and sorted file 1, giving big sorted file. So this file should then contain the combined data of sorted file 1 and 2 in a sorted way. Let's try this out. All right, so these are the two unsorted tables. And because the result is written to a file, I can't immediately display it here, but I will dump it to the terminal. Yes, so here, as you can see, I used age with an ascending key. So now I start with the youngest going to the oldest. And that's why Maggie Simpson comes first here and Mr. Burns comes last, just the other way around as we had it in the previous examples. And you can see they're taken from different files. Maggie appears in the first data set, Mr. Burns appears in the second data set, and they're all combined in this big data set here. And you can check that all of them are there. The Flanders, the Simpsons, Smithers, and Barney Gumble. They're sorted by age, and the second key was the last name in descending order. So here actually we should have Homer coming before Ned Flanders, because the last name in descending order, Simpson, comes before Flanders. So we see the merge procedure works just fine if we apply it to sorted data sets. And that's it. We indeed made it to the end of the video. Thanks for watching. I hope you really enjoyed this video and learned something. And don't forget to like it and subscribe to my channel. See you in the next chapter.